Okay, we've talked about a couple of quantities that get conserved, okay, in nature. One of them is linear momentum, right? We talked about conservation of momentum. If you have a closed system, okay, there's no outside force acting on your closed system, then by golly, the total amount of linear momentum is not going to change. And actually, if you think about our universe as a closed system, then the total amount of momentum in our universe is fixed. I mean,
wait, wouldn't it be like all funky with all that relativity stuff? Right?
No, it works. Momentum works even with funky relativity stuff. And in fact, the net linear momentum of the universe is 0. So there is no momentum in the universe. Total. So that's kind of a cosmic perspective. But anyway, then we talked about conservation of energy. How much energy there is in the universe. Turns out that that's conserved as well. Energy in all its forms. We did specific problems with conservation of mechanical energy under special circumstances. But if you include internal energy and radiation, all the different forms that energy comes in, the total amount of energy in the universe is fixed. And I think I read somewhere that the total amount of energy in the universe is actually 0. But I don't know. It's because gravity, I don't know. Let's not get into that. Now there's a third quantity that we're going to conserve. You're going to see this is conserved for an isolated system where there's no outside force, no outside torque acting on it, and that would be angular momentum. So let's get to it. First of all, let's talk about angular momentum of a rigid body. Here's what we did. We defined angular momentum, L, as being R cross P. Okay? And we said that this was R mv sine phi. And you use the right-hand rule to get the direction of that. Okay, well, if we have a rigid body, let's take a look at some blobby shape here. And so here's my blobby shape. Here's my x-axis and my y-axis. And let's say that here's my axis of rotation, and this thing is just going to rotate around the z-axis, which is coming right out at us. By the way, the direction of the z-axis is defined to be the the cross product of x cross y. You know, you get z. That's called the right-handed axis system. Okay, so the z-axis coming out at us. And let's take a look at a little particle of this. We'll call that mi. Or we could call it dm if we wanted to. We could use calculus to do this. And here's ri. And what you would do if you're a computer science major, or if you're a physicist modeling this, because you can't really do, for a blobby shape, calculus is pretty useless. I mean, calculus is great if you've got lots of symmetry and you can use analytical tricks to solve it. But really what you need is numerical calculus, which is actually a computer program that breaks this up into thousands of little pieces and treats it as a system of particles. And some of you become computer science majors, you'll be doing this kind of thing a lot. This is something computers do really well. But anyway, if this thing is rotating with a certain angular velocity omega, then this particle, or this part of the mass of my blobby shape, has a velocity. And that velocity is equal to Ri, that's the Vi, is equal to Ri times omega. Now notice I don't put an I next to the omega, right? Because if this is a rigid body and the rigid body is rotating with an angular velocity of omega, everything on the object, except the point at the axis of rotation itself, everything there is rotating with an angular velocity of omega. Omega is constant for everything. So what I can do, if I'm looking at Li equals the summation of all my little individual angular momenta, the momentum of each little particle, well, that's going to be Ri cross MIVI, right? But what is VI? Well, I'm going to substitute that in there. And this becomes, is equal to, and by the way, let's just say we don't even need to worry about the cross product anymore, because with a rigid body with an axis of rotation, the velocity is going to be perpendicular to R. I mean, it's just going to be. So we don't have to worry about the angle between R and P is going to be 90 degrees in every case. So that's just going to go away because the sine of 90 degrees is 1. And so I can say that this is equal to R M V, and V is R omega. Well, what is this? If I sum these all up. Well, if I sum these up, this is R squared M omega. And omega doesn't need to be in the summation. I can factor it out. And look what I've got here. I've got the summation of Ri squared Mi. Now this should look familiar to you. What is mass times the radius squared? That's rotational inertia. And so we can say that L for a rigid body is equal to I omega. And omega has an orientation in three-dimensional space, so it is considered a vector of sorts. And so L equals I omega. And this is what we talked about before. You know, this is like the linear analog of P equals mv. So if you have a rigid body, it's going to have this angular momentum. So if you know, now by the way, this angular momentum is as measured from the axis of rotation. Now, did you, now in this object that I just drew right here, notice that the axis of rotation is not at the center of mass of the object. So what do you have to use to find the rotational inertia of an object if the axis of rotation is offset from its center of mass? Do you remember? It was one of the videos, and because we didn't have time to get to it, right? And I said, watch the video online. Yes, it's called the parallel axis theorem. So this could be equal to, well, I, here it could be equal to I of the center of mass plus md squared, where d is the distance from the axis of rotation to the center of mass location on the object. So there's d right here. So don't forget about the parallel axis theorem. Okay, go back and review that. Now this brings up an interesting situation. And it's, and that is this. If we have L equals I omega, it's a product of I, of the rotational inertia and the angular velocity. Now, we've said before that there is a torque. If you have a torque acting on an object, if you have a net torque on an object, well, that's going to be equal to dl dt, the rate of change of angular momentum. Well, now if I apply that to this product right here, I get I d omega dt plus di dt times omega. Okay, we just apply the product rule. Now, if you have a rigid body, what's true? Well, a rigid body means it's not changing shape. So I stays constant, and so this goes away. And so this becomes the net torque equals I, and what is d omega dt? I alpha. That's the angular acceleration, which makes sense. This is the net force equals mass times acceleration, right? For the yeah.
Do all of Newton's laws like have an angular analog, so an object that's spinning will remain spinning unless the torque is active upon it?
I think it might be too much to say all of the linear things have angular equivalents, but just about everything that we dealt with has a rotational equivalent. Yeah. I don't know if it's everything, but a lot of things do. Okay. Now here's a situation that doesn't apply. This all applied to a rigid body, but I'm going to just say in general, if the net torque on an object is equal to 0, then L is constant. Now, in this statement, there's no need to consider it a rigid body anymore. If I've got an object, an extended body that can move, that can change its shape, like a human body, if you can change shape, then you have a certain angular momentum, but if there's no net torque, then the angular momentum isn't going to change with time. It's torque that changes the angular momentum of an object, whether it's a rigid body or a system of particles or what. So if the net torque on an object, whether it's a rigid body or a system of particles or whatever, is 0, then we can say that L is constant. Well, if the angular momentum is constant, then L initial equals L final. Well, if this is true, then let's say I have a non-rigid body, but it can, but there's no torque on it. That means that I initial omega initial must be equal to I final omega final. Now this is a conservation of angular momentum. If there's no net torque on an object, whether rigid or a particle or a system of particles, if there's no net torque, period, the total angular momentum of your system will not change with time. It will remain a constant. Now imagine, have you ever seen an ice skater? And an ice skater will go into a spin, and then you have your arms and legs out, and then you bring your arms and legs in. You're reducing, when you bring your arms and legs in, you reduce your rotational inertia, and therefore you have to spin faster. That's kind of like this. The rate at which you change, you're going to, well, no, I'm sorry. God, I need to redo these videos. Don't think, scratch that. just imagine this. If I reduce my rotational inertia, I have to increase my angular velocity if there's no net torque on my system. And this is what happens when an ice skater or a dancer pulls in his or her arms and legs closer to the axis of rotation. They spin faster. They have to, because they've reduced this, because the product of rotational inertia and angular velocity has to be constant. That's conservation of angular momentum. Okay, and we're actually going to demonstrate that right now, but not on the document camera, sorry.